Okay, students. So, in this lecture, till now, we have completed these topics: phenomena of refraction of light, apparent depth, total internal reflection, and refraction through spherical surfaces. Now, let's take our last topic, that is lens maker's formula and power of lens. Okay, so let's see here. So, this is the formula we derived in last lecture, and this is the formula for refraction through a spherical surface. Okay. So I hope you all understand that how the refraction happens in a spherical surface and how to derive the formula for this refraction through spherical surface. Now move forward to our next topic, and the next topic is lens maker's formula. Okay, now for the lens maker's formula, let's see, this is the lens. Okay, you can see this is a convex lens. Okay, and there are two surfaces of this convex lens. This, let's say, this surface is surface 1, and the radius of curvature for this surface 1 is r1. Okay, and this is a surface 2, and radius of curvature for this surface 2 is r2. Done. Okay, and the refractive index outside the lens is called mu m. What is the mu m? Mu m is the refractive index of the medium. Okay, the refractive index of a medium is mu m, and refractive index of the lens, mu l. Okay, mu l is the refractive index of the lens. Understand? So this is the convex lens, and this O is called optical center. This O is the optical center. Okay, so this convex lens is having two spherical surfaces. This red one is the spherical surface 1, green one is the spherical surface 2. The radius of curvature for this surface 1 is r1. Radius of curvature for this surface 2 is r2. Okay, and mu m is the refractive index of the medium outside the lens, and mu l is the refractive index of the lens. Okay, so let's move forward. So this is the object, and this object is placed here. This O is a object. So O is we denoted by optical center. So let's give it another, any other name. Okay, uh, let's say this one is M. So I'm denoting M as a object. Okay, so this M is my object. Now what happens? The incident ray comes from this object. Let's say this one is an incident ray, and this incident ray incident at this point on the spherical surface 1. So this is the incident ray. Let's draw a normal here. So this is a normal. Okay, so this is a normal. Now what happens? I'm take considering this. Okay, mu m is less than mu l. Okay, we are considering this case that refracted index of medium is less than refracted index of lens material. Okay, so outside is a rarer. Okay, so this outside medium is a rarer medium, and inside is a denser medium. So when the light ray travels from rarer medium to denser medium, it bends towards the normal. Okay, and this is a normal. This green one is a black one is a normal. So this light ray bends towards the normal. So let's make a refracted ray like this, so it bends towards the normal. Let's see, like this. Okay, so this is a refracted ray from this spherical surface 1. Okay, if I extend it in a, if I extend it like this, so it will form the image at this point, and let's say this image is I1. Okay, understand? This is the spherical surface 1. This is this M is my object. Okay, let's say, let's say uh, O is a object, this O is a object, and P is a point here. Okay, so this happens, this image is formed because of this spherical surface 1. Okay, this image is formed I1 because of this spherical surface 1. Okay, now let's see this distance from object to this point P. This object, this distance is called U, object distance, and this distance P to image 1 is called V1. Okay, again I am repeating that. What is I1? I1 is the image of this object formed by the first spherical surface. Okay, now this ray reaches at this point. Okay, now draw a normal. Let's draw a normal at this point. This is a normal at this point. Okay, now this is a normal at the spherical surface 2. Now this light ray is traveling from denser medium to, this is the denser medium. It is traveling from denser medium to rarer medium. So when it travels from denser to rarer, it goes away from the normal. This is a normal. Remember the thing, this is the normal. So this light ray goes away from the normal. So when it goes away from the normal, we'll get the image, another image like this. It goes away from the normal. Let's say the image is formed here. So this is the image I2. Okay, and this image is formed because of this second spherical surface, and its distance from point P is, let's say this distance is V. Okay, so this I2 is the final image. Again I am repeating, this O is a object, this is a lens, this is the first spherical surface, its radius of curvature is R. This is the second spherical surface, its radius of curvature is R2. Okay, this is the light ray incident at this spherical surface 1, so that the image formed here at I1, and from second spherical surface image formed here at I2. Okay, the distance is U. The distance of first image is V1. The distance of second image is V. So now apply this formula, refraction through a spherical surface. We already studied in the last lecture. So apply these formulas for, let's apply it for the spherical surface 1. Spherical surface, or okay, this first spherical surface is spherical surface 1. So for spherical surface 1, what is mu1? So I just mentioned you in my last lecture when we were deriving the formula for refraction through spherical surface. The mu1 is the refractive index where the incident ray lies. So this is the incident ray. So this mu1 is equal to what? Mu1 is equal to mu m. Okay, and mu2 is what? Obviously mu2 is a mu l. Okay, so apply this formula. So mu2 by v. Okay, so mu2 is what? Mu2 is mu l. Okay, and v is the, so image formed by the first spherical surface is I1, and its distance is what? V1. So mu l divided by v1. Okay, then minus mu1. Mu1 is what? Mu1 is mu m. So this mu m divided by u is equal to mu2 minus mu1. So mu2 minus mu1 means mu l minus mu m. Okay, and divide by r. So radius of curvature for this spherical surface is r1. So we'll get this equation. Okay, okay. I hope you all understand this. Now let's write for the spherical surface 2. Spherical surface 2. Okay. Now for spherical surface 2, the incident ray lies in a, this lies in a lens, or in a, in this medium. So here the refractive index is what? Mu l. So mu1, we will take mu1 is equal to mu l, and mu2 is what? Mu2 is equal to mu m. Okay. Now here, if I apply the formula for the refraction from the spherical surface, so mu2 is what? Mu m. So mu m divided by v. Obviously, this distance, this is the image formed by the second surface, and its distance is what? V. So mu m by v. Okay, and then minus mu2 by mu1. You can see the formula, mu2 by v minus mu1 by u. So mu1 is what? Mu l. Okay, now what is u here? So what happens? The image formed by the first spherical surface is walked as the object for the second spherical surface. Understand? Got it? The image formed by the first spherical surface, this I1, the image formed by the first spherical surface is walked as the object for the second spherical surface. So the object distance, what we will take object distance v1. So this v1 is a object distance. So here for the second spherical surface, so this is v1. Now mu2 minus mu1. So mu2 is what? Mu m. minus mu L. Then radius of curvature is what? R2. So this is R2. So we get these two equation. This is first equation and this one is a second equation. I hope you all understand. Okay. Now let's move. Let's add both these equations. So we'll get add equation add equation 1 and 2. Okay, add equation 1 and 2. So we'll get mu L divided by V1, okay, minus mu M divided by U plus mu M divided by V minus mu L, okay, mu L divided by V1 is equal to mu L minus mu M divided by R1, then plus mu M minus mu M minus mu L divided by R2. Okay, so you can see from here mu L by V1, mu L by V1, it cancel out. So you'll get minus mu M by U, okay, plus mu M by V is equal to, I can write mu L minus mu M divided by R1. Take minus sign here. So minus, I can write it as mu L minus mu M, okay, divide by R2. Okay. Further, we can write it as minus mu M by U plus mu M by V is equal to mu L minus mu M and 1 upon R1 minus 1 upon R2. Okay. From here, I can take mu M as common. So I can write 1 upon V minus 1 upon U. Okay. So from like we can write mu L minus mu M. Okay. 1 upon R1 minus 1 upon R2. Now this formula 1 upon V minus 1 upon U is called Lenz's formula. Okay. Lenz formula. So this formula 1 upon F is equal to 1 upon V minus 1 upon U. So this formula is called Lenz formula. So I can write from here 1 upon F, 1 upon F is equal to mu L minus mu M divided by mu M, then 1 upon R1 minus 1 upon R2. And what is this? But mu L minus mu M. Okay, so this step one, further step we can write 1 upon F is equal to mu L by mu M minus 1, okay, and 1 upon R1 minus 1 upon R2. And from this I can write that 1 upon F is equal to, what is this, mu L by mu M? Okay, so mu L by mu M is, we can say that refractive index of lens with respect to medium. So mu L M minus 1, and from here I can write 1 upon R1 minus 1 upon R2. Okay, so by this way we can get the formula, and this formula is called lens. Okay, so this formula is called lens makers formula. Okay, this is the derivation for lens makers formula. What is the lens makers formula? 1 upon F is equal to mu Lm minus 1, 1 upon R1 minus 1 upon R2. What is mu Lm here? Mu Lm is mu L by mu M, means refractive index of lens with respect to medium. Actually, when you can see this diagram, in this diagram ultimately what is happening, my object is placed at this point O and final image is formed at this point I2. Okay, so I can say that the light ray is traveling from this medium to the lens and then lens to the medium. Okay, so here this incident ray is traveling from medium to lens. So I write the refractive index of lens with respect to medium. Okay, Here the light ray is traveling from medium to lens, so we write mu lm, refractive index of lens with respect to medium. I hope you all understand. So this is about the lens maker's formula, and this is the derivation of lens maker's formula. Okay, and there are like various cases we can explain by using the lens maker's formula. Like let's see one of some cases I'm taking here. uh, let's say if I have a plano convex lens like this is the plano convex lens. Okay, this is the plano convex lens. So in plano convex lens, let's say this radius of curvature for this surface is r1, and this r2. So this r2 will be equal to infinity. Okay, the radius of curvature for the plane surface is infinity. So if you put the values here, you will get acha, outside medium is take air, so medium is air, so I am taking 1, and here the refractive index for lens I am taking mu. So if I put all these value, I will get what, 1 upon f is equal to mu minus 1. Okay, mu l is mu m is 1. I am taking it as air, medium is air, so mu minus 1, and from here what I will get, 1 upon acha. Here also learn about the sign convention for this radius. So how we take the sign conventions for this radius of curvature. So you know that this direction is we take as positive, and this direction we taken as negative. So wherever the mouth of this spherical surface is open, you can see the, I can say, I just for remembering I'm saying that let's say this mouth is opening towards the positive axis. So because this mouth is opening towards the positive axis, we take this radius as plus, and take it as r, plus r. Okay, so this is 1 upon r minus 1 upon infinity. So from here I can write 1 upon f is equal to mu minus 1 divided by r, and from here I can write f is equal to r divided by mu minus 1. Okay, so these, there are number of cases we can solve by using this lens maker's formula. Let's say I have a equiconvex lens. Equiconvex lens. What is the equiconvex lens? Equiconvex lens is a lens in which the radius of curvature of both the spherical surface is same, like r1 is equal to r2 is equal to r. Okay, so this is the equiconvex lens. This is, let's say this is the equiconvex lens. So here this one is my first surface. It is R1 is equal to R. This is my second spherical surface. So R2 is equal to R. Now, how we take sign, which one is positive and which one is negative? So you can see that this is direction is positive direction. This direction is negative direction. So this mouth is opening towards the positive direction. So it will take, this is taken as positive, and this mouth is opening towards the negative direction. So this is taken as negative. Now apply the formula. So we'll get 1 upon f is equal to, again I'm taking the same case that the medium is air, so mu is, this one is 1 and this one is mu. So the formula becomes mu minus 1, and from here 1 upon r1 means 1 upon r. Okay, then minus 1 by r. Okay, like this. So what you will get, mu minus 1, so 2 by r, and from here I can say that f is equal to r divided by twice of mu minus 1. Okay, so you can see that, and I hope you all understand that how to take the sign for this radius of curvature. Now let's define here also the power of lens. What is power of lens? Okay, so what is the power of lens? Power of lens is the, what is the power of lens? Power of lens is a ability of a lens to converge or diverge the incident light ray. This is the definition of power of lens. Okay, what is the definition of power of lens? Power of lens is a ability of a lens to converge or diverge the incident light ray. Okay, and mathematically the power of lens is the reciprocal of focal length. Okay, mathematically power of lens is a reciprocal of focal length, like this 1 upon f. And if this f is in meter, the unit of, the SI unit of this Power of lens is diopter. So D is called diopter. Understand? Now, if this f is given in centimeter, if given in centimeter, most of the cases it is given in centimeter. So if this f is given in centimeter, you just multiply it by 100. So you'll get in answer in diopter. Okay. So what is power of lens? Power of lens is the ability of a lens to converge or diverge the incident light ray. Okay. Mathematically, it is the reciprocal of focal length. If the focal length is given in meter, formula is simple, p is equal to 1 upon f. But if the focal length is given in centimeter, then we write 100 divided by f centimeter. The SI unit of power of lens is diopter. Okay, what is diopter? So I can write the lens maker formula also, p is equal to 1 by f. Okay, so it is equal to mu l divided by mu m minus 1. Okay, and here 1 upon r1 minus 1 upon r2. Okay, now let's take the last example for this lecture. So you all know about our sunglasses. You can see that the sunglasses are like this. The spherical surfaces in sunglasses are like this one and this one. Okay, so let's say this one is radius of curvature is r1, and for this radius of curvature is r2, and the radius of curvature is same for both the spherical surfaces. So here the r1 is taken as plus r, and here r2 is taken as plus r as a sign convention. Okay, I already explained you how to take sign conventions. Okay, positive, negative. So if I want to find out the power of this sunglasses, so power is equal to mu l by mu m minus 1. Now 1 upon r1. So r1 is what? Plus r. So 1 upon r1 minus 1 upon r2. R2 is also plus r. So we'll get this one 0. Okay. So this one is what? 1 upon r minus 1 upon r 0. So power is 0. So you all know that the power of sunglasses is 0. Okay. So I hope you all understand the derivation and the concept and how to take the sign conventions for the radius of curvature. Okay. Okay then. Thank you.